students, now we'll start the new chapter, probability distribution. This chapter is for 5 marks for the board examination. I will explain all the theoretical parts, solve example and all the examples given in the exercise. Now let us start. Now let us start. A random variable is a real valued function defined on sample space of a random experiment. In other words, the domain of a random variable is the sample space. म्हणजे डोमेन मध्ये काय घेणार तर आपण सॅम्पल स्पेस घेणार त्यामध्ये सॅम्पल स्पेस ऑफ रॅन्डम एक्सपेरिमेंट व्हाईल कोडोमेन इज a set of real number. Now see this here. The domain, this is S. Okay, this is the domain. It's a sample space. And what about its a codomain? Codomain is a set of real number. And what is that X? X is a random variable. We will define it. It have different definitions. When we toss the coin, if I like the head, then I will consider that the head occurs on that toss. If I say that I want the tail, then tail occurs on that toss. Okay. In this way, X is a random variable defined on the sample space S. S is called the domain and R is called the codomain. Okay. Thus, X is defined as from the set of sample space to the set of the real number is a random variable. We often use the abbreviation RV to denote a random variable. Consider an experiment where 3 seeds are sown in order to find how many of them germinate. Every seed will either germinate or will not germinate. Let us use the letter Y when a seed germinates and the letter N when a seed does not germinate. The sample space of this experiment can then be written as S. That is Y. It means that all the 3 these seeds will germinate. Next YN. That is the 2 will germinate and 1 will not germinate. And in this way we get all the N 8 points. This is the sample space when we toss the coin 3 times. At that time we get the 8 sample point. In a similar way, here n of x is equals to 2 raised to 3 and that's equals to 8. None of these outcome is a number. We shall try to represent every outcome by a number. Then how we can do it? Consider the number of the times the Y letter appear in a possible outcome and denote it by X. Okay. Then how many times Y occurs for the first, second, third up to the 8. Now see this here. X means what number of the times Y occur. Sometimes you may take N occur. Therefore here X occurs. Number of the times X occurs means what? All the seeds, 3 seeds are germinated are 3. Next 2 are germinated. Then here is a 2. Next 1 is a germinated. Then this is 1. And the last is none of them is germinated. That is a 0. Here X is very important. How many of them are germinated? The variable X has 4 possible values. Namely, not a single will germinate, 1 will germinate, 2 will germinate and 3 will germinate. The set of possible values of X is called the range of X. Thus, in this example, the range of X is the set 0, 1, 2, 3. A random variable is usually denoted by a capital letter like X or Y. Here we have denoted the random variable by X. A particular value taken by a random variable is usually denoted by the small letter X. Note that X is always a real number and the set of all possible outcomes corresponding to the particular value of X of x is denoted by the event. That is a particular, it is nothing but the event. That is capital X is equals to x. For example, in the experiment of 3 seeds, the random variable x takes the 4 possible values, namely 0, 1, 2, 3. Okay. The 4 events are then defined as that x is equals to 0. None of them is germinated. Then this is a n and n. 1 is germinated. Then 1 is y is there. 2 is germinated. Then double y is there. And 3 germinated. Then 3y is there. Note that the sample space in this experiment is finite, and so is the random variable is also finite. A sample space need not always be finite. For example, the experiment of tossing a coin until a head is obtained. If I say to you to toss the coin until head occurs, then suppose that if you toss the coin, you will get head, no problem. If you toss the coin, you are not getting the head. First you get tail, and then you are trying for, then you are getting the head. In third toss, in third experiment, it may be possible that you will get first toss is a tail and then head. There may be the possible that you will get tail and then edge. This will be the possibilities. Note that S contains an unending sequence of the tosses required to get a head. Here, S is countably infinite. Suppose that any one of them, he tried to get the head, but he get the tail, and after 5th time, he get the head. So maybe the happens that if anyone toss the coin, he tossed the 6 times and then 7 times he get the head. And in this way, you will get the infinite. Okay. The random variable x is defined from the set of sample space to the real number, denoting the number of the tosses required to get a head has the range 1, 2, 3 in this way, which is countably infinite. What is there? X is defined from S to R, denoting the number of the tosses. Here this is the first toss, second toss, third toss. And in this way you can get the infinite, countably infinite. Now next is the types of random variable. There are 2 types of random variable, namely, one is first is a discrete random variable, okay, and second is continuous random variable. Now what is meant by the discrete random variable? A random variable is said to be discrete random variable if the number of its possible values is finite or countably infinite. The values of a discrete random variable are usually denoted by non-negative integers. That is 0, 1, 2, 3 up to infinity. Examples of the discrete random variables includes the number of children in a family, the number of patients in a hospital ward, the number of cars sold by a dealer, the number of stars in the sky, and so on. Note that the values of discrete random variable are obtained by counting. What is meant by the continuous random variable? A random variable is said to be a continuous random variable if the possible values of this random variable form an interval of a real number. A continuous random variable has uncountably infinite possible values, and these values form an interval of real numbers. Examples of continuous random variables include the heights of trees in a forest. It may be the varies. It may be the varies from the 1 meter to the 10 meter, and there are the continuous. That may be the fraction and fraction and fraction. Weight of the student in a class, daily temperature of a city, speed of a vehicle, and so on. The value of the continuous random variable is obtained by the measurement. This value can be measured to any degree of accuracy, depending on the unit of measurement. This measurement can be represented by a point in an interval of real number. The purpose of defining a random variable is to study its properties. The most important property of a random variable is its probability distribution, and this is nothing but this is the name of this chapter, that is the probability distribution, how it is distributed. Many other properties of a random variable are obtained with the help of its probability distribution. We shall now learn about the probability distribution of a random variable. We shall first learn probability of a discrete random variable and then learn the probability distribution of a continuous random variable. Probability distribution of discrete random variable. Let us consider the experiment of throwing 2 dice and noting the number on the uppermost faces of the 2 dice. The sample space of this experiment, that is S1112, and in this way, and last is 66, and n of x is equals to 36. Let x denotes the sum of the 2 numbers in any single throw. Then what will be the sum of what is the minimum sum? Minimum sum is 1 plus 1. And what will be the last maximum? 6 plus 6. That is a 12. Therefore, 2, 3 up to the 12 is the set of all possible values of x. Further, that is x is equals to 2. Then what is the sample space? It's 1, 1. X is equals to 3. 1, 2, 2, 1. And x is equals to, and in this way, x is equals to 12 is only the 6, 6. Next, all of these 36 possible outcomes are equally likely if the 2 dice are fair, that is, if each of the 6 spaces have the same probability of being the uppermost when the die is thrown. As the result, each of these 36 possible outcomes has the same probability, which is 1 upon 36. This leads to the following result. P of capital X is equals to 2. Then what is its sum? P, that is 1, 1. It's the probability 1 upon 36. P of capital X is equals to 3. That sum is 3. Then what are the points? That is 1, 2, 2, 1. Then it is a 2 upon 36. P of capital X is equals to 4. Then 1, 3, 2, 2, 3, 1, 3 upon 36, and so on. The following table shows the probabilities of all possible values of x. When 2, it's 1 upon 36. When 3, 2 upon 36. 4, 3 upon 36. And in this way, you will get all the probabilities. Such a description giving the values of the random variable x along with the corresponding probabilities is called the probability distribution of the random variable x. This table is called the probability distribution of the x, random variable x. In general, the probability distribution of a discrete random variable x is defined as follows. The probability distribution of a discrete random variable x is defined by the following system of numbers. Let the possible values of x be denoted by x1, x2, x3, and the corresponding probabilities is denoted by small p1, p2, p3 up to, where pi is equals to p of capital X is equals to xi, where I is equals to 1, 2, 3. Now a discrete random variable can have finite or infinite number of possible values, but they are countable. Sometimes the probability distribution of a discrete random variable is presented in the form of order pairs of the form. That is, x1 has a probability p1, x2 has p2, and in this way. A common practice is to present the probability distribution of a discrete random variable in a tabular form as shown in below. What is the first? Xi. P of capital X is equals to xi. X1 has probability p1, x2, p2, and in this way. Here, if xi is the possible values of x and pi is equals to p of capital X is equals to xi, then there is an event ei in the sample space S such that pi is equals to P of EI, then that event may be different types of the events. Since Xi is the possible values of capital X and Pi is equals to Pi of capital X is equals to Xi, it is a positive. Also, all the possible values of X cover all the sample point in the sample space S, and hence the sum of their probabilities is 1, and that is all the probabilities are greater than or equal to 0. This is very important for all I, and the sum of Pi is equals to 1. Sum of all the probabilities, that is equals to 1. Now the definition. Let the possible values of a discrete random variable capital X be x1, x2 up to the xn with the corresponding probabilities Pi, where I is equals to 1, 2, 3 up to n. If there is a function f such that Pi is equals to P of capital X is equals to Xi is equals to f of Xi for all possible values of X, then f is called the probability mass function, that is the PMF of X. Now next, the cumulative distribution. This is the PMF, that is the probability mass function. Next, cumulative distribution. The probability distribution of a discrete random variable can be specified with the help of the PMF. If it is a continuous, it is sometimes more convenient to use the cumulative distribution function, that is the CDF of the random variable. The cumulative distribution function, that is the CDF of a discrete random variable, is defined as follows. Then what is that? It's a definition. The cumulative distribution function, that is the CDF of a discrete random variable capital X, is denoted by the capital X and is defined as like this. That is, capital F of X is equals to P of capital X less than or equal to small x. That is summation, that is Xi is less than X and the summation of all these probabilities. Okay, where F is the probabilities mass function, that is the PMF of the discrete random variable. With the help of the examples, you will definitely understand this concept. What is a CDF? Okay, तुम्हाला उदाहरणाच्या सहाय्याने अधिक हे चांगलं समजणार आहे. And you have find out the cumulative statistics मध्ये तुम्ही cumulative tables बघितले असतील, त्याच प्रकारे ही cumulative CDF आहे हा cumulative distribution function. Now next, for example, consider the experiment of tossing 4 coins and counting the number of the heads. We can form the next table for the probability distribution of X. Okay, that is counting the number of the heads. X is equals to, now the coin is tossed 4 times, therefore there are the 5 values: 0 head, 1 head, 2 head, 3 head and 4 head. Okay, then it's a probability. If the 0 head, then 1 upon 16. Next, 1 head, 1 by 4, 2 head, 3 by 8, 3 head, 1 by 4 and 4 head, that is 1 by 16. Now see this, the first is 0 head. 0 head is possible only the single time. When you toss the coin 4 times, then you will get the sample number of the sample point is 16. That is a 2 raised to 4. 2 raised to 4 is 16. 0 head you will get the single time. 4 heads you will get the single time. But what about the 1 head? 1 head you will get the 4 times. Okay. And in this way 2 head and the 3 head. 3 head you will get again the 4 times. And what about here? That is, if you multiply here numerator denominator by 2, then you will get 6 upon 16. That is the 2 heads you will get the 6 times. And in this way you can construct this table. And what about its cumulative distribution? What about its CDF? That is, first 1 upon 2 is as it is. Next is this 1 upon 2 plus 1 by 4. 1 upon 2 plus 1 by 4, you will get 3 by 4. Next, this 1 by 8 plus 3 by 4, you will get 7 by 8. Again next, 1 by 16 plus 7 by 16, you will get 15 by 16, and last is 1 upon 32 plus 15 upon 16, and then you will get 31 upon 32, and in this way you can construct this table. Also, next, see this. It is possible to define the several types of the random variables on the same sample space. If two or more random variables are defined on the same sample space, their probability distribution need not be the same. Their probability distribution will be different. For example, consider the experiment of tossing a coin twice. The sample space of this experiment, capital S is equals to HH, HT, TH and TT. Let X denote the number of the heads obtained in two tosses. Then X is a discrete random variable and its value for every outcome of the experiment is obtained as follows. That is, if we select the head, then for the HH, its value is 2, HT, TH is 1 and TT is 0. Let Y denote the number of heads minus the number of the tails in the two tosses. Then Y is a discrete random variable and its value for every outcome of the experiment is obtained as Y. Now see this here. In this toss, we have both are HH, therefore it is a 2 minus 0 because tail is 0 there. Head is 2, therefore here is 2 minus 0 and that is equals to 2. For the next HT, here head is 1, tail is 1, 1 minus 1 is 0. For this also, head is 1, tail is 1, 1 minus 1 is 0. And for the last, it is a TT, head is 0 and tail is minus 2 and therefore it is a minus 2. And in this way, you can define another random variable Z, which is such that is equals to the number of heads upon the number of tails plus 1. Then the Z is also a discrete random variable and its a value for every outcome of the experiment is obtained as follows. Now first is Z means what? The number of the heads, that was in first experiment, it is a 2. Okay. Number of the tails is 0. 0 plus 1, that is 1 and you will get 2 here. Therefore here is a 2. What about the second? Number of the head is 1 and the number of the tail plus 1, that is 1 plus 1. Then you will get 2 here, that is equals to 1 upon 2, 1 upon 2 for this. And what about the last? The last is number of the head, here is a 0. Okay. Number of the, when we consider TT for this, when we consider the TT, the number of head is 0 and to the denominator, number of the tail is 2 plus 1. But here number to the numerator there is a 0, 0 upon 3 and you will get 0 here and hence here is a Z of TT that is equals to 0. These examples show that it is possible to define many distinct random variables on the same sample space. Possible values of a discrete random variable can be positive or negative, integer or fraction. These examples show that it is possible to define many distinct random variables on the same sample space. Possible values of a discrete random variable can be positive, negative and the integer. I have repeated it. Okay, now see this, the first example. Two persons, A and B, play a game of tossing a coin thrice. Okay, two persons, A and B, play a game of tossing a coin thrice. If the result of a toss is head, A gets ₹2 from B. And if the result of a toss is a tail, then B gets ₹1.5 from A. Now let X denotes the amount gained by or lost by A. Show that X is a discrete random variable and show how it can be defined as a function on the sample space of the experiment. Now see this here. X is a number whose values depend on the outcome of a random experiment. Therefore, X is a random variable. Since the sample space of the experiment has only 8 possible outcomes. Okay. X is a discrete random variable. Now the sample space that we know from the 10th standard. The values of X in rupees corresponding to these outcomes of the experiment are as follows. If there is head, then you will get 2 into 3. That is the 3 heads are there. And therefore 2 into. If he gets the head, then A will get the 2 into 3. That is equals to 6. Now see this here. H, H, T, H, T, H. And next is the T, H, H. What's happening here? You are getting the 2 heads minus. But second party is getting 1 tail. Then you have to give the 1.5 to him, the another person. Therefore 2 into 2 minus 1.5 into 1. And then that's it. So value is a 2.5. And next is a HTT. Therefore A will get the 2 into 1. And the loss of again 1.5 into 2. That is equals to minus 1. And last is a TTT. Then minus 1.5 into 3. Then loss is that is a minus 4.5. Here a negative amount shows a loss to the player A. This example shows that X takes a unique value for every element of the sample space, and therefore X is a function on the sample space. Further, the values of X are 4.5, 1, 2.5 and the 6. Now next. Now the next example is a bag contains 1 red, 2 green balls. One ball is drawn from the bag at random. Its color is noted and then ball is put back in the bag. One more ball is drawn from the bag at random and its color is noted. Let X denotes the number of red balls drawn from the bag as described above. Derive the probability distribution of X. Now see this here. Let the balls in the bags be denoted by red, green 1 and green 2. The sample space of the experiment is then given by this is that is a 2 raised to 3 and that is here not 2 raised to 3. Then these are the RR, RG1, RG2, R1, sorry G1R, G2R, G1, G2. Next is also G1, G2. I will repeat again here. The first is red, RG1, RG2, G1R, G2R, G1 and again G1, G1, G2, G2, G1 and last is G2, G2. Since X is defined as the number of red balls, we have for the first X, RR is to RG1, RG2, G1R, G2R that is equals to 1 and the last is that is the next is a G1, G1, next is a G1, G2, G2, G1, G2, G2 and that's equals to 0. No red is there. Thus X is a discrete random variable that can take the values 0, 1, 2, 0, 1, 2. Okay. Therefore 0, 1, 2 and their probabilities that is a 4 upon 9. Next is a also 4 upon 9 and the 2. When the 2 reds are there, that is a 1 upon 9. 2 cards. Again I will repeat here. 2 cards are drawn. Now see this again. 2 cards are randomly drawn with the replacement from a well-shuffled deck of 52 playing cards. Find the probability distribution of the number of X drawn. Okay. Now the solution. The number of S drawn. Let x denote the number of days among the two cards drawn with the replacement. Then what are the possibilities of the x? That is a 0, no x is there, 1s is there, 2s is there. Are the possible values of x? Since the draws are with replacement, the outcomes of the two draws are independent of each other. Also, since there are the 4s in the days of 52 cards, therefore, when all are 4, the probability of the s is 4 upon 52, that is equals to 1 upon 13. Non-s, that is a 48 upon 52, then you will get 12 upon 13. What is you will get here? That is a non-s, then you will get 48 upon 52, and its a fraction is a 12 upon 13. Then now next, see this here, x is equals to 0, no s is there, none s, first is none and second is also none. Then what about its probability? That is a 12 upon 13. Next is also 12 upon 13, because it is a with replacement. Therefore, probability of x is equals to 0 is 144 upon 169. When one s is there, that is first is s, second is non-s, first is a non-s and second is s. Then you will get, when there is a s, then 1 upon 13 into 12 upon 13 plus 12 upon 13 into 1 upon 13, and if you simplify it, then you will get 24 upon 169. When x is equals to 2, then the probability of s and both are the s, that is 1 upon 13 into 1 upon 13, that is 1 upon 169. Okay. The required probability distribution is then as follows. When both are the non-s, then it is a 144 upon 169. When one s is there, then it is a 24 upon 169. When both are the s, then it is a 1 upon 169. Okay. See this here. A fair die is thrown. Let x denote the number of the factors of the number on the upper face. X denotes the number of the factors. Find the probability distribution of x. The sample space of the experiment is factors पाहिजे x. Now see this, s is 1, 2, 3, 4, 5, 6. That is for the fair die is thrown. The values of x for the possible outcome of the experiment are as follows. For the 1, its a factor is 1. For the 2, its a factor is 2. 2 factors are there for the 2. For the 3, 1 into 3, 3 into 1, that is the 2 factors. Here is a 2. For the 4, there are the 3 factors. Okay. Now, for the 5, again there are the 2 factors. And for the 6, there are the 4 factors. That is the number of the factors of 1. I will repeat again here. Number of the factors of 1 is divisible by 1 only. 2 is divisible by 1 and 2. 3 is divisible by 1 and 3. 4 is divisible by 1, 2 and 4. 5 is divisible by 1 and 5. And 6 is divisible by 1, 2, 3 and 6. And in this way. That is P1, that is the probability of x is equals to 1. Then here is a 1 upon 6. Then P2, probability of x is equals to 2. Then the 2 factors are, that is here is a 2, 1, 2 and 3. Total are 6. That is a 3 by 6. And the 3 factors are, okay, 3 factors are only P4. That is 1 upon 6. And the 4 factors are the P of 6, which is 1 by 6. The probability distribution of x is then as follows. That is the values of x is 1, 2, 3, 4. Its first is probability is 1 by 6. And 2 factors is 3 by 6. Again 3 factors are 1 by 6. 4 factors are again 1 by 6. Find the probability distribution of the number of doublets in 3 throws of a pair of dice. Let X denotes the number of doublet. Possible doublet in a pair of dice are 1 1, 2 2, 3 3, 4 4, 5 5 and the 6 6. Okay. Since the dice are thrown thrice, then the 0, 1, 2, 3 are the possible values of X. The probability of getting the doublet in a single throw of a pair of dice is, that is P is equals to, if you are getting the doublets, then it's 1 by 6. And what about the Q? If you are not getting the doublet, then it is a 1 minus 1 by 6, which is 5 by 6. Now see this here. The P, X is equals to 0. That is, no doublet is there. Then your throw is a 3 times. Then Q and Q and Q. 5 by 6 into 5 by 6 into 5 by 6. Which is 125 upon 260. Next is P of capital X is equals to 1. One doublet is there. Then what are its possibility? First you will get doublet. Then next 2 is not possible. Next middle is possible. Then last is possible. If we add it, then you will get 3 PQ square. Substitute the value of P and the Q. Square it, multiply it, then you will get 75 upon 260. When X is equals to 2, that is the 2 doublets are there. Here, doublet, doublet, non-doublet, doublet, non-doublet, doublet, and non-doublet. This is doublet and doublet. Then here you will get 3P square Q, and you will get 15 upon, if you substitute the value of P, which is 1 by 6, and the value of Q is 5 by 6, and perform their multiplication, then you will get 15 upon 260. When you will get the 3 doublets, that is, 3 doublets means what? 1 by P, 1 by P, 1 by P. The possible values, that is, the P is 1 by 6, 1 by 6, and 1 by 6. 1 into 1 into 1, and 6 into 6 into 6. Then you will get 260. The probability distribution of X is as follows. The next problem. What is the probability distribution? For the value of X is 0 is 0.1, 1 is K, 2 is 2K, 3 is 2K, and 4 is a K. Then first find the value of K. The table gives the probability distribution, and therefore the sum of all the probabilities, that is equals to 1. Therefore first is 0.1 plus K, next is a 2K, next is also 2K plus K, its a sum is 1. And you will get, that is a 6K is equals to 0.9, and hence the value of K is a 0.50. This is 0.50. Find the probability when X is less than 2. Then you will get, that is, P of X is equals to 0 and X is equals to 1. For X is equals to 0, it is a 0.1, and for 1, then it is a K. Add it. What is the value of K? K is a 0.15. Substitute it. And therefore, probability of capital X less than 2 is a 0.25. For the probability capital X greater than or equal to 3, then it is X is equals to 3, X is equals to 4. Okay. Therefore, for X is equals to 3. Okay. For X is equals to 3 is a 2K, and this is a 4. 2K plus K. Then you will get 3K. That is a 3 into 0.15. You will get 0.45. Next, the values of X lies between 1 to 4, equal to 1 and not equals to 4 also. Therefore, we will take the values of X is 1, 2 and 3. Therefore, when X is equals to 1, it is a K. X is equals to 2, it is a 2K. It's a given. Okay. In the table, you have given X is equals to 1, it is a K. X is equals to 2, it is a 2K. Okay. If we add it, X is equals to 3 is again 2K. If we add it, then you will get 5K. 5 into 0.15, then you will get 0.75. Next, here is a cumulative, that is a CDF. Probability of capital X is less than or equal to 2. Then addition of this, all this, that is X is equals to 0, X is equals to 1 and X is equals to 2. 0 is 0.1, 1 is k and 2 is again 2k. If we add it 0.1, 2k, then you will get 0.1 plus 3 into 0.15, and overall you will get its addition is f of 2 is equals to 0.55. Next, expected value and the variance of a random variable. In many problems, it is designed to describe some feature of a random variable by means of a single number that can be computed from its probability distribution. Few such numbers are mean, median, mode, and variance, and the standard deviation. In this section, we shall discuss the mean and the variance only. Mean is the measure of location, or it's a central tendency in the sense that it is roughly located a middle or the average value of the random variable. And this type of the mean you have learned in statistics in the 10th standard also. Definition: let x be a random variable whose possible values are x1, x2, x3 up to the xn. Occurs with the probabilities. Their probabilities are p1, p2, p3 up to p1, pn respectively. The expected value or the arithmetic mean of x, denoted by e of x or the mu, is defined as e of x is equals to mu, I is equals to 1 to n xi into pi. That is x1 into p1, x2 into p2, x3 into p3 plus dash dash, and the last is xn into pn. In other words, the mean or expectation of a random variable capital X is the sum of the products of all possible values of x by their respective probabilities. Now it's a definition. Next, let x be the random variable whose possible values x1, x2 up to the xn occur with their probabilities p1, p2 up to the pn. Now the next is, here we will define the variance. Let x be a random variable whose possible values x1, x2, x3 up to the xn occur with the probabilities p1, p2, p3 up to the pn respectively. The variance of x, denoted by variance of x and the sigma r, is defined as the variance of x summation I is equals to 1 to n in bracket xy minus mu bracket square in bracket into pi. The non-negative number, that is sigma suffix x is equals to root of variance of x, is called the standard deviation of random variable capital X. We can also use the simplified form of the variance of x is summation I is equals to 1 to n xi square into pi minus summation I is equals to 1 to n xi pi bracket square. Therefore, the variance of x is equals to e of x square minus e of x bracket square, where I is equals to 1 to n xi pi xi square into pi is equals to e of capital X square. Now the examples. 3 coins are tossed simultaneously. X is the number of the heads. Find the expected value and the variance of x. Solution. When the 3 coins are tossed, this is the sample space. X is equals to, what is here? Find the expected value. X is the number of the heads. Then the first is number, its values are 0, 0 head, 1 head, 2 head, 3 head. Then xi, 0 head, 1 head, 2 head, 3 head. Then its probabilities 1 by 8, xi into pi, that is 0 into 1 by 8 is 0. Next is xy square into pi, xi square into pi, that is also 0. Next is 1 into 1 by 8, then you will get 3 by 8. Next is xi square into pi, then you will get 3 by 8. Next is, you can perform this, all these multiplication, xi into pi for these 2 heads, okay, for 3 heads, which is 1 by 8 and 3 by 8 and 9 by 8, and their summation I is equals to 1 to n xi pi is equals to 12 upon 8, and I is equals to 1 to n. Xi square into pi, that is a 24 upon 8. Now see this here, the expected value I is equals to 1 to n, xi pi is equals to 12 upon 8, that is equals to 1.5. Now the variance of x, I is equals to 1 to n, xi square into pi minus I is equals to 1 to n, xi into pi bracket square. The values of xi into pi, that is a 24 upon 8, next is 1.5 bracket square, and if you simplify it, then you will get variance of x is equals to 0.75. Next example, let a pair of dice be thrown and the random variable capital X be the sum of the numbers that appear on two dice. Find the mean or the expectation of x and the variance of x. The sample space of the experiment consists of 36 elementary elements in the form of the order pairs xi, yi. Xi, the values of xi are 1, 2, 3, 4, 5, 6, and y are also same 1, 2, 3, 4, 5, 6. The random variable capital X is, that is the sum of the numbers on the two dice takes the values. That is a 2, 1 plus 1, 2, 3, 4, 5, and the last 4, 5, 6, 7, 8, 9, 10, 11 or the 12. The maximum is the 12. Minimum is the 2. Now here the two values. Then it's a possible only the 1 upon 36. Now xi pi, that is a 2 upon 36. Xi square into pi, you will get 4 upon 36. And in this way, there is a, when xi is equals to 2, 3, 4, 5, you can construct this table by considering xi pi, xi square into pi square. From this table you can understand this. Okay. Now see this here, all these tables and their summation. What is the summation? Xi into pi, where I is equals to 1 to n. That is a 252 upon 36. There is a sum of all these elements. See this here. Sum of all these elements, 256 upon 36. And next is a summation of I is equals to 1 to n xi square into pi. That is a 1974 upon 36. And that is a 54 upon 54.83. And therefore E of x is equals to I is equals to 1 to n xi pi is 7. And the variance of x, summation I is equals to 1 to n xi square into pi minus summation I is equals to 1 to n xi pi bracket square. And here 54.83 minus 7 square, which is 54.83 minus 49. And here you will get the variance of x is a 5.83. Now the next example, find the mean and the variance of the number randomly selected from 1 to 15. That is, you have the numbers 1 to 15 and you are asked to select the number. The sample space of this experiment is S is equals to 1 to 15. X denotes the number selected. Then X is a random variable which can take the values 1, 2, 3 up to the 15. Each number selected is equiprobable and therefore the probabilities of all these numbers is 1 upon 15. And their sum, that is a 1 plus 2 plus 3, and in this way, that is a into 1 upon 15. And therefore the expected value of this is nothing but, by mistake it is a, now see this here, all the numbers have equiprobable, therefore p of 1 is p of 2, p of 3 and p of 15 is equals to 1 upon 15. Now the mean, a of x is equals to I is equals to 1 to n xi pi. 1 is 1 upon 15, 2 is also have the probability 1 upon 15, 3 is also have the probability 1 upon 15, and in this way last 15 into 1 upon 15. Select, that is a take 1 upon 15 as a common, then sum of 1 plus 2 plus 3 plus 4 plus up to the 15. That is a sum of all 1 plus 2 plus 3 plus dash dash plus 1 upon 15 into 1 upon 15. Now sum up all these by using the arithmetic progression. You will get n into n plus 1 upon 2. That is a 15 into 16 upon 2. And after calculation, you will get the 8 there. And next is the variance of x. That is I is equals to. Here is a variance of x. Variance of x. I is equals to 1 to n xi square into pi minus I is equals to 1 to n xi pi bracket square. And then you will get that is 1 square into 1 upon 15, 2 square into 1 upon 15, and in this way. And this is nothing but the r square, sum of the r square. Then what is that? Summation of the r square is n into n plus 1 bracket complete in bracket 2n plus 1. But what is the value of n here? N is 15. Here is a n. N plus 1 means what? 15 plus 1. And next is a 2n plus 1. That is a 15 into 2. 30. 30 plus 1, which is 31 upon 6. That is a summation of r square. That formula you know from the 11th standard. N in bracket n plus 1. And here is a 2n plus 1 upon 6. And here is a 8 square. And therefore after calculation, you will get variance of x is a 82.67 minus 64, and you will get 18.67, and hence the variance of x is a 18.67. Next problem, two cards are drawn simultaneously or successively without replacement from a well shuffled pack of 52 cards. Find the mean, variance and the SD standard deviation of the number of the kings drawn. Let x denotes the number of the kings in a draw of the two cards. X is a random variable which can assume the values 0, 1, 2. Okay, then the P of x is equals to 0. That is a no king. No card is king. That is a 48C2 upon 52C2. No king. That is there are the 4 kings. None kings here. 48C2, 58C2. Then you will get here that is a 188 upon 221. You can simplify this. That is you have learned in the 11th standard permutations and the combinations. Next, 1 king is there. That is exactly 1 king is there. From the 4 king, you can get 1 king, and from the remaining 48, you can select 1 card. That is 4C1 into other than kings. This is a 48C1, and after simplification, you will get 4 into 48 into 27 upon 52 into 51, and overall you will get 32 upon 221. हे तुम्ही कॅल्क्युलेशन करू शकता. एक किंग पाहिजे असेल, हा एक किंग आहे, हे अदर दॅन नॉन किंग आहे, and you are drawing the 52C2, 2 cards are drawn. हा तुमचा तो सॅम्पल स्पेस आहे. Next is a 2 kings, that is a both are king. 4 cards, 4 kings are there, that is 4C2 upon 52C2. This again is a sample space, and after simplification you will get 4C2, the value of 4C2, that is 4 into 3, 52C2, that is 52 into, or overall after the calculation you will get this. This you are learning the 11th standard. I will not show now this here. Therefore P of, then the P of capital X is equals to 2, that is equals to 1 upon 221. Now here we will start the exercise 7.1. The previous part was very big one because the previous knowledge and the description given for the probability distribution, mean, variance and the standard deviation, probability mass function and cumulative distribution, that we have learned. Now we will start the exercise 7.1. Let x represent the difference between the number of random variable capital X heads and the number of the tails when a coin is tossed 6 times. What is that? Let x represent the number of, that is the difference between the number of random variable x heads and the number of the tails when the coin is tossed 6 times. What is the possible values of x? Okay, when a coin is tossed 6 times, okay, the number of the heads can be no head for the 6 times, then its value is 0. 1 head may be the possible in 6 times. 2 head may be the possible in 6 times. 3 head may be the possible. 4 head may be the possible. 6 head may be the possible. Okay. 5 head, 6 head may be the possible. Okay. Therefore, when a coin is tossed, let's say 6 times, the number of heads can be 0, 1, 2, 3, 4, 5, 6. The corresponding number of the tails. When there is a 0 head, then here is a 6 tails, 5 tails, 4 tails, 3 tails, 2 tails, 1 tail, 0 tail. We require the difference. X represent the difference between of the random variable x, that is a head, and the number of the tails when a coin is tossed. Now their difference, that is a 0 minus 6, which is minus 6. Next is here is a 1 minus 5 corresponding value. Here is a 0 minus 6. 1 minus 5, 4. 2 minus 4 is minus 2. 3 minus 3 is 0. 4 minus 2 is 2. 5 minus 1 is 4. 6 minus 0 is 6. Therefore, the x takes the values, the random variable takes the values minus 6, minus 4, minus 2, 0, 2, 4 and 6 in this way. Next, an urn contains 5 red, 2 black balls. 2 balls are drawn at random. X denotes the number of the black balls drawn. Okay. What are the possible values of x? You can see this was the problem. Urn contains the 5 red and the 2 black balls. 2 balls are drawn at random. X denotes the number of the black balls drawn. Then what are the possible values of x? That is 2 and 5. 5 red and the 2 blacks. If the 2 balls are drawn from that urn, it may be contain either 0 or 1 or the 2 black balls. Therefore, x can take the values 0, 1, 2, and this is the answer. Next, state which of the following are not probability mass function of a random variable and give you a reason. Now see this probability distribution. The values of x are 0, 1, 2 and the p of x is 0 0.4, 0 0.4 and the 0 0.2. The PMF of the random variable should satisfy the following condition. Again, I will repeat here. The PMF, probability mass function of random variable, should satisfy the following condition. The probability of all the values must lie between 0 and 1 and the sum of the probability is equals to 1. Now see this here. All the values are positive. The first condition is satisfied. What about the second condition? Sum of all the probabilities. 0.4 plus 0.4 plus 0.2, that is equals to 1. And hence p of x can be regarded as the PMF of the random variable capital X. Next, the values of x are 0, 1, 2, 3, 4 and the p of x is 0.1, 0.5, 0.2, 0 minus 0.1, 0.2. Now see this here, the probability of 3, which is a minus 0.1, it is a negative, which does not satisfy our condition that the value of the pi must lie between or equal to 0 and 1. And hence the p of x cannot be regarded as probability of mass function of the random variable capital X. Now the next is, see this table, the values of x are 0, 1, 2 and their probabilities are 0.1, 0.6 and 0.3. Now all these probabilities lies between 0 and 1 equals to 0 and equals to 1. And what about their sum? Their sum is equals to 1. Therefore, hence the p of x can be regarded as the PMF of the random variable capital X. Next, z 3, 2, 1, 0, minus 1 and their probabilities are given also. What about their sum? Their sum is 0.3, 0.2, 0.4, 0, 0.05, which is equals to 0.95 and that's equals to, doesn't equals to 1. And hence p of z cannot be regarded as PMF of the random variable z. Next, the random variable z takes the values 3, 2, 1, 0, minus 1, and their values are also given. And if we add it, I think that it is repeated. Okay, no problem. Its value is not equals to 1, and therefore P of Z cannot be regarded as the PMF. Next problem, that is the fifth problem now. The random variable var, its values is minus 1, 0, and 1. What about their probabilities? 0.6, 0.1, and 0.2. If we add it, then summation of the PR, which is not equals to 1, it is a 0.9, and therefore P of Y cannot be regarded as the PMF of the random variable Y. Now next is sixth problem. The values of X are 0, minus 1, minus 2. What about their probabilities? 0.3, 0.4, 0.3. All the values lies between 0 and 1, and sum is 1. Therefore, P of X can be regarded as the PMF of a random variable. Okay. Next, find the probability distribution of first the number of heads in 2 tosses of a coin, the number of tails in simultaneous tosses of 3 coins, the number of heads in the 4 tosses of a coin. Now see this here. The first, the number of heads in the 2 tosses of a coin. For the 2 tosses of a coin, the sample space that we know, HH, HT, TH, and TT. Let X denote the number of heads in the 2 tosses of a coin. Then X can take the values 0, 0 head, 1 head, 2 head. Therefore, P of X is equals to 0. When 0 head, it's possible one time, whose probability is 1 by 4. Okay. Next, 1 head. 1 head is possible 2 times. That is a 2 upon 4. That is equals to 1 upon 2. 2 heads. That is a single time. Therefore, it is 1 upon 4. This is a sample number of the sample point. The probability is 1 by 4. The required probability distribution is, that is the values of X are 0, 1, 2, and their corresponding probabilities are 1 by 4. 1 has probability 1 by 2. 2 has probability 1 upon 4. Next problem. The number of the tails in the simultaneous tosses of 3 coins. Therefore, their regular sample space S is equals to. Okay. This is S is equals to. Let X denotes the number of the tails. The number of the tails is 0 tail, 1 tail, 2 tail, 3 tail. 0 tail, it will happen. 0 tail म्हणजे कुठे? Okay, all are here heads. Therefore, it happens only the single time, one time. 1 tail, it's a 3 times. That is a 3 by 8. 2 tails, again 3 by 8. And 3 tails, it's again 1 by 8. The required probability distribution is, that is a 0 tail, 1 tail, 2 tail, 3 tail, 1 by 8, 3 by 8, 3 by 8, and 1 by 8. And in this way, we get the probability distribution. Next, the number of the heads in the 4 tosses of a coin. When a fair coin is tossed 4 times, then the sample space is H, 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 T, H, H, T, H. Okay, in this way you will get the 16 points. Okay, that is a 2 raised to 4. You will get the 2 raised to 4, and here you will get the 16. When anyone say that toss the coin thrice, then 2 raised to 3 means what? 8. Anyone say that toss the coin twice, then you will get the 4 sample points. And in this way you are getting the 16 n of S. Okay, let X denotes the number of the heads. Then X can take the values 0, 0 head, 1 head, 2 head, 3 head, 4 head. X is equals to 0. This happens when? That is a T. That is a n of X is equals to 1. Single time. Next is it's a probability n of X upon n of S, which is 1 upon 16. Next is 1 head. It happens 4 times. That is n of X upon n of S is equals to 4 upon 16. Its a probability is 1 by 4. 2 heads. Then in this way you will get this the random variable X, and n of X is equals to 6 here. Okay, and therefore it's a probability, that is when there are the 2 heads, capital X is equals to 2, Then n of x upon n of s is a 6 upon 16. That is nothing but 3 upon 8. Next, when capital X is equals to 3, that is a 3 heads, then you will get the random sample space of event of this is, that is the 4 points are there. N of x is equals to 4. Therefore, that is in this set that there are the 4 elements. That is the P of capital X is equals to 3 is a n of x upon n of s, which is the n of x is 4. 4 upon 16, that is equals to 1 by 4. When x is equals to 4, all are heads. This happens only the single time. And therefore, it's a probability of n of x upon n of s, and that is equals to 1 upon 16. And hence, the probability distribution of capital X is as follows. 0 head 1 upon 16, 1 head 1 by 4, 2 head 3 by 8, 3 head 1 by 4, and the 4 head 1 by 16. And in this way, up to the question number 4, I am completing here. Now, the remaining question will be in the next video. Now, we'll see in the next video. Till then, goodbye.